The next talk is from Professor Manoli Sava from Simon Fraser University. Unfortunately, I think he cannot join us, but he sent in advance one video of his talk. So, Sijuan, can you please?
Yeah, I will play the video for him.
Yeah.
Can you hear me?
Yes.
Okay. So, wait a minute.
Yeah, we see your screen.
Good. So.
Hi, and thank you for inviting me to give this talk at this workshop. The title of the talk is 3D Simulation for Embodied AI, Three Emerging Directions. So first of all, I want to say a little bit about what I mean when I say 3D simulation and embodied AI. When I say 3D simulation for embodied AI, I mean taking a physically embodied agent that takes actions in the real world, such as a robot, and then simulating that, approximating it in a virtual setting as a virtual embodied agent taking actions in a virtual world. And of course, this is quite a popular approach nowadays. 3D simulation for embodied AI has found many uses in a variety of communities. Robotics, of course, but also natural language processing, studying language grounding problems, mapping instructions to visual navigation, to follow those instructions in real simulated environments, and so forth. So it's very popular nowadays. It's used in many research tasks and many communities. My entrance into this area of work was through the AI Habitat project, which was a project in 2019 involving a number of people from a number of institutions looking into establishing a platform for embodied AI research. So that's where my perspective is coming from. And at the time, what the AI Habitat effort focused on is simulating these kinds of visual navigation episodes in reconstructed real environments, like the ones that you see here, from the replica, the Matterport 3D datasets, and other similar kinds of reconstructions of real spaces. So this was the kind of 3D simulation that was being done, and a big focus of this effort was to do it efficiently. So in comparison to prior work at the time, some of which you see here in these bar charts, the focus was to enable much higher simulation rates, much higher frames per second of rendered visual navigation experience, exceeding thousands of frames per second on single GPU devices, especially when parallelized on a commodity GPU. One could reach upwards of 10,000 frames per second. And why was this important at the time? It was important because we could go from some regime where the findings of a particular experiment were in a particular way, where we were contrasting traditional SLAM-based approaches for visual navigation against learned approaches, to a different regime by just expanding the horizontal axis here, the amount of experience, by enabling experiments with much more experience. We could observe trends where now learned agents based on reinforcement learning could start to exceed the performance of traditional SLAM-based visual navigation agents. So this increased speed led to new findings, in essence. But this, of course, effort was a while back, and it was only a first step. And for me, it's that nowadays there's a continued interest in 3D simulation platforms to enable a variety of different tasks. Here you see a few examples, and definitely not an exhaustive list of recent efforts to establish new 3D simulation platforms, focusing on a variety of different tasks. So there's a lot of excitement around the use of 3D simulation. And I see three emerging directions in 3D simulation that I will try to articulate in this talk: scalability, predictivity, and interactivity. I will try to describe these directions from my perspective, from work that I have been involved in, but I believe these are general trends that are taking place in the community right now, the community leveraging 3D simulation for embodied AI. So the first direction, towards greater scalability. This is essentially a continuation of expanding the end of the spectrum in terms of the speed of simulation and the scale of simulation. So allowing us again to go into previously not possible experiments, experiments that were previously not practical to run due to speed or scale limitations. And a good example of this direction is the DDPPO project. This was a project that was led by Eric Wiemans, PhD student at Georgia Tech, and presented at last year's ICLR. So in this project, which has the title Learning Near Perfect Point Goal Navigators from 2.5 billion frames, we examined distributed RL systems methods and asked the question of how can we enable good scaling of 3D simulation, complex 3D simulation in the distributed RL setting. And of course, there's two main paradigms for doing this. There is asynchronous distributed RL, where rollout workers simulate experience and communicate with a parameter server asynchronously, what you see here on the left. And then there's also synchronous distributed RL, where rollout workers synchronously communicate with one another. And the key challenge in these settings is the variability in the experience collection runtime. So some workers may take longer to simulate a particular episode of experience compared to other workers. This is a key challenge from the perspective of the systems design for distributed RL systems. Now, with the DDPPO project, what we wanted to do was to enable better scaling by getting as close as possible to this idealized synchronous setting where all workers take the same amount of time. And our insight was that it's possible to preempt the slower, the straggler workers by cutting off experience collection if a certain point in time is reached, and then just using all available experience thus far. Even with this really simple idea, we saw that that led to good scaling. So here you see a plot of number of GPUs on the horizontal axis against the speed up relative to baseline 1 GPU on the vertical axis. Ideal is, of course, this y equals x line. A naive method has approximately this kind of performance here that you see in the red line, and the idea behind the DPPO led to increased scaling, so closer to ideal scaling. With this better scaling, we could then investigate a setting where we really push the frontier of the amount of experience given to learned visual navigation agents, trying to get to these near perfect point, goal, task, visual navigation systems. And here you see a plot of, on the horizontal axis, pushing the limit of the amount of experience, going up to billions of frames of experience, and then reaching near perfect visual navigation performance on unseen environments, which at the time was a rather impressive result. Just to give you an idea of what this looks like, here's an example test episode from an environment, previously unseen environment, where the agent navigates from one point down a corridor, through a house, through this residence, turning left, and then going to the target, which is, I believe, a bathroom in the back of the house. So this episode was carried out in a previously unseen environment, and it's actually quite surprising to see this level of performance, this fairly efficient navigation through a complex realistic environment. And just to take a closer look at a particular snapshot from this episode, let's pause here where the agent is going down this corridor, and then look at this indication of where the goal, where the target is. The bathroom at the back of the house is in front of the agent, but at the same time, the egocentric perception of the agent shows that there is an obstacle. There is this wall, this bookcase up against the wall directly in front. And then to the left, there is what looks like the doors that lead to outside. And so the right decision is to turn right once it's possible. And indeed, this is what the agent does. It takes a right turn when it reaches that point, and then proceeds through this other corridor and then to the back of the house. So quite impressive that this level of efficiency can be achieved on unseen environments, previously unseen environments. And of course, this was all enabled by massive amounts of experience collected through large-scale experiments through this DDPPO system, which allowed near linear scaling by preempting these slower worker processes. And through 2.5 billion steps of experience accumulated in these experiments allowed us to reach near perfect navigation performance on unseen environments. But fortunately, the performance follows a roughly power law-like distribution. So we get 90% of the navigation performance from only 10% of the training. And so that means we don't really have to push it to the extreme all the time in this way. So that was the first direction that I see. And of course, there's newer work as well that continues to push the limit of scalability. And here I want to transition to the second direction by asking this question. Is scale and speed all that we need? You know, if we have very speedy simulation and high scale experiment setups, is that all we need? Well, not really. There's another important thing that we should care about. And this is, I think, exemplified by another direction of recent work, which I summarize here with the word predictivity. And what does this mean? It's really trying to communicate this importance of the sim to real transfer, that we really, at the end of the day, want to deploy real systems, real robotic systems in the real world to perform a task. We shouldn't just stick in the simulation regime. We should care about, do we learn something that is useful in a real world setting? And, you know, as this example from the DARPA challenge tries to show, we're quite far generally from that goal of real systems performing well in the real world. So here I'll use this project as an example. This is a project by Abhishek Kadian and Juan Trong, and this was presented at last year's ICRA. Are we making real progress in simulated environments, measuring the sim to real gap in embodied visual navigation? And in this project, the general idea was that we could go out to the world and acquire a real environment, acquire this space with some obstacles in it, virtualize it. And then after we have this virtualized environment, we could simulate episodes, navigation episodes in this virtualized version of the real environment. With the ability to simulate these episodes, we could then begin to set up these equivalent parallel episodes in simulation and in reality, where on the left you see a simulated mobile-based robot navigating in the simulated, in the virtualized environment, and then on the right you see an equivalent episode of the real robot navigating in the real world. With these equivalent episodes, we could then begin to establish a correlation between reality and simulation. Here you see a simple way to visualize that, a plot where on the horizontal axis we have the success rate of simulation episodes, and then on the vertical axis we have the success rate of real episodes, equivalent real episodes. And points in this plot are different methods. So we see here how the performance of a method correlates between simulation and reality. And the key idea of this work was that we could actually fine-tune simulation parameters to make the simulation more predictive of the real performance of different methods and how different methods would be ranked in simulation. That would become more predictive to the real ranking by fine-tuning our simulation parameters. And this is what you will see here in this animation. By playing around with simulation parameters, we could reach a much higher correlation between measured performance in simulation and performance in reality. So this was the general idea of this work. And it also actually allowed for an interesting form of debugging, where using this kind of insight of treating simulation as something that could be optimized, we could identify important parameters that actually lead to catastrophic failures in reality. Important parameters that if we change in simulation, they will make the simulation much less predictive. This is a visualization of one such important parameter. The ability of an agent to slide along obstacles in simulation was something that was very detrimental to the predictivity of simulated performance. So it's not very well in alignment with reality. And that was an interesting finding from this piece of work. So to summarize, this virtualization of environments allowed for this parallel simulation to reality episode setting. And this allowed us to establish this correlation between simulation and reality, and then use that correlation to optimize simulation parameters that would lead to better predictivity of the simulation. So this, of course, I'm omitting a lot of detail. So I refer everybody, if they're interested, to look at the original publication for the finer detail of these experiments. Now that we discussed speed, scale, and predictivity, are we done? Isn't everything great now? Is there anything to do after this point? Well, we're not really done, because everything that I've been showing so far is completely frozen in place. All of these visual navigation episodes, both in the first and second sections of this talk, completely frozen. There is nothing happening between the agent and the environment. There is no interaction, in other words. And that is a big limitation. That is a big limitation that much recent work in 3D simulation has been trying to alleviate. So this is what I call the towards interactivity direction that I see emerging in recent work. We saw some examples of this earlier, some recent work that proposed 3D simulation platforms that allow interaction, rich interaction with simulated environments, like the two examples that you see here. And there's, of course, more challenges to be tackled in this space. There are actually some very interesting research challenges. One of the challenges is that interaction has many levels of detail. You can view interaction at many levels of abstraction. You can care about fine detail grasping, multi-contact grasping simulation, or maybe you care at a much more abstract level of interaction where you can symbolically open and close, cabinets and look for objects. So the level of abstraction is an important thing that influences system design and the capabilities of a simulation platform. Another big challenge for work in this area is that there are few interactive 3D environments. They are hard to design or hard to capture from the real world. And an additional challenge from the systems perspective is that simulating the physics of interactive 3D environments is in general quite slow. So these are a number of challenges. And here I would like to share with you a bit of a brief overview of some rather exciting ongoing work on a continuation of the Habitat platform to address these challenges, the so-called Habitat 2.0 effort. And the first step of this effort was to create a set of richly interactive environments by taking photorealistic reconstructions like the ones you see on the left, the replica dataset, and creating an interactive human-authored, artist-authored version of the environment, what you see on the right here. So a direct counterpart, again, establishing a bit of a virtualized version of reality, but now fully interactive. So this was a first step of this effort to create this so-called replica CAD data set. And then in this data set to implement a platform that allows for rich and yet fast, very efficient interaction between an agent, such as the fetch robot that you see here in the bottom left, equipped with a number of egocentric sensors. You see these stacked up on the right here, a pair of RGB and depth cameras on the robot, simulate this efficiently. So here you see an example episode of this mobile-based manipulator, the fetch robot, moving around, opening drawers, taking objects out, picking them up and placing them elsewhere, going over to the fridge, opening the fridge, taking some objects out, and so forth. And a big focus of this effort is to make these kinds of experiments very, very fast and very efficient. So here you see a brief summary of a performance comparison against prior work, where we observe orders of magnitude of improvement in terms of the steps per second, the physical steps per second that can be simulated. So this is an exciting effort that involves many people, of course, and I would like to take a second here to acknowledge that it's not me, that's doing most of the work. It's a large team of folks, and I would like to conclude with some takeaway messages, where I would like to say that 3D simulation is a powerful tool that can enable much work in embodied AI and robotics, but it should definitely not be treated as a black box. There are many important characteristics and parameters of simulation that should be carefully investigated. Improving the speed and scalability of simulation matters a lot because it allows us to do experiments that were previously not practical, and it allows us to investigate new regimes and to acquire new findings. Simulation parameters can be viewed as something that can be optimized to allow for better predictivity, better ability to correspond to reality. And then lastly, this simulation of richly interactive 3D environments is a very interesting and challenging frontier for embodied AI. So that's pretty much it. Thank you everyone for your attention, and definitely feel free to get in touch if any of this is interesting or if you have any questions. And I'd like to end here briefly by having a brief a plug for the visual computing group at SFU, which is a very rich set of faculty with interests in visual computing and embodied AI and robotics. So if you're ever in Metro Vancouver, once we get back to normal, definitely get in touch and definitely feel free to visit us. Thank you all so much for your attention. I hope you enjoyed this talk.
Okay, thanks, Sijuan. So you saw the contact details for Manolis. Please feel free to get in touch with him.